Hi, welcome back. In this video, we're going to talk about how to find the x and y intercepts and the domain of a function, of a rational function. Remember, as our previous few videos, we're going to focus specifically on the x and y intercepts, although we could still look at vertical asymptotes, the holes, that kind of stuff. I will be graphing those other components to it, but if you have questions specifically about how did you find the asymptote or how did you find the hole in that problem, know that there's a video for each of those topics. Yeah. All right. So let's get to it. Whenever you see a rational function, right, and trying to find the x and y intercept, we first want to focus on the meaning of an x and y intercept. So if we have a graph, the x-intercept anywhere on the graph, whether it's positive or negative, we know that the y value will always be 0, right? It could be anywhere on the graph. The x-intercept, the y is equal to 0. Yeah. And similarly, what do we know about y-intercepts? Well, whenever it crosses, here I'll put an x-axis, I'll put a y-axis. When it crosses the y-axis, anywhere on the y-axis, like pick a y value, say this is 7, we're going to have x is going to be 0, and y is going to be up here at the top. You can also choose a negative value. No matter where you choose, the x value will always be 0, right? So we're going to keep these things in mind. For y-intercept, the x value is 0. This information will help us find the x and y-intercepts of our functions. So let's get to it. We're going to do, 3, 4 examples. At the very end, I'm going to show you how to find the domain. So if after 2, feel free to fast forward, go to the very end of this video, and you can watch how to talk about the domain of the function. All right. So here we have an example. As usual, whenever you start these problems, right, we want to factor and simplify the rational function. So we can account for the holes, we can account for all the things that are there. So on the top, we're going to factor out a 2, meaning we're going to divide everything by 2. Divide that by 2, you get x squared. Divide the 10 by 2, you get positive 5x. Divide the 12, you get positive 6. Right? We always want to simplify as much as possible, and we can start by removing or factoring out a value if possible, because that'll make this piece factorable a little bit faster. Now the factors here are going to be x plus 2, x plus 3. And for the denominator, you're going to have x plus 2, x plus 1. Now, if you want to do this on the side, and you want to go about finding out the factors, feel free to use the column methods that I showed you, right? 2 times 3. You can do the same thing for the denominator. The more you do these practice examples, the more you practice with me and yourself, the faster you're going to get to identifying the factors. Now here we can tell that there's going to be a hole at x equals negative 2, and you can watch a video on that if you like. And the function simplifies down to 2x plus 3 divided by x plus 1. Now, from this alone, I know that we have an asymptote at, let's see, negative 1. Right, that's the denominator, our vertical asymptote. I know that there was a hole at x equals negative 2, so I'm going to put a hole here somewhere. Yeah? Let's talk about how to find the x and y intercepts. Right, this method that we did here, these steps, we want to make sure that we are able to do that before finding any attribute of a rational function. Before you find x and y intercepts, before you find holes and vertical asymptotes, always start with these steps, right? Always. And then we can talk about what we're here to talk about. Let's talk about x-intercepts. Now, no matter where it lands on the x-axis, the y value, right, like say it stands here, the y value will be 0. So it'll be x comma 0 for y. Which means I can take my function, my simplified function, this right here, and I can replace the y value with 0. This will allow me to now solve for x. What x value, when I solve for it, results in a y value of 0. We get rid of the denominator, right? We can multiply both sides by x plus 1. Excuse me. 0 times anything is 0. Yeah, the whole denominator goes to the other side and it cancels with the 0. I can solve for x here by distributing. 0 equals 2x plus 6. Now I can just solve for x. Yeah, divide both sides by 2. And we get x equals -3. Or if you want to write it as a coordinate pair, or as a point, you can write it as -3, 0. So this will be an x-intercept. Sometimes we have multiple x-intercepts. In this case, we have one x value at the end. Yeah. Now, briefly, why were we okay with the x plus 1 completely disappearing and turning into 0? Well, we have to multiply by the denominator, but why is it okay that we're not thinking about why this value disappears? Well, if you think back, we have a vertical asymptote at -1. So there's already going to be nothing existing in that part of the graph. So when we multiply by 0 and it disappears, we're not affecting the problem at all because we already knew there was nothing there. Yeah. All right, let's talk about the y-intercept. Now, very similarly, we're going to take our problem, and now to find the y-intercept, we know that the x value is 0. So we're going to replace x with 0. Take your simplified function, and anywhere you see an x, replace it with 0. And now we just simplify. Yeah. Do a little bit of PEMDAS. 0 plus 3 is 3, so we're left with 2 times 3. 0 plus 1 is 1. 2 times 3 is 6, and 6 divided by 1 is just 6, right? So the output is 6. When x is 0, the output is 6. So you can write it as a coordinate point as well, 0, 6. We know that it's going to cross the y-axis over here. Now, we're not going to go into all of the details of this graph, but hopefully we can see, right, as we go through this problem, we're going to graph something like this. The graph will point downward. It'll get really close. Something like that. And then we said there was a hole at -2, so we would have a hole down here somewhere at -2. That doesn't exist. Yeah. I'll be doing an example at the very end where everything is put together. Okay? For now, and by the end, I mean at the end of this unit, for now, we're just looking for the x and y intercepts. All the other stuff, hopefully, is a recap of what we've done before. All right. Here we have another example. Very similarly, right, we can factor the problem. We can simplify it. We can reduce this problem by dividing everything on the top by 3. And we get x squared plus 5x plus 6. In the bottom, everything is divisible by 6, so I can take out the 6. And that gives me x squared plus 3x plus 2. Now I can factor this quadratic a little bit faster, right? Because I see 2 times 3 will give me 6, and it'll also add up to 5. So we got 3 times x plus 2 and x plus 3. In the denominator, I have 6 times x plus 2, x plus 1. Yeah, I can see that there's going to be a hole at x plus 2, or the hole will be at x equals -2. And then this simplifies down to 1/2. So the function can be simplified to x plus 3. This is just 1/2, right, over 2 times x plus 1. This is the simplified function that I'm going to be working with in order for me to find the x and y intercepts, right? Plugging in 0 here versus up here, it's not only just faster, but this also accounts for the fact that there's a hole. If you plug 0 in the original equation, you may or may not be finding more x-intercepts than you need, because this does not account for how many holes, right? we want to make sure that we simplify it so that we don't accidentally count an x-intercept as something that exists on the graph when in reality there is a hole there. All right, let's find the x-intercept. We're going to replace the y value with 0. Right, and remember that with the y-intercept, we're replacing the x value with 0. And if you ever forget, just go to a graph, pick a point, 0, 8. I know that the x value is 0, so then I can find the y-intercept. Okay, so I'm going to replace y with 0, right? Y with 0. So 0 equals x plus 3 divided by 2 times x plus 1. I replace the y with 0. And I can multiply both sides by the denominator so I can solve for x. This cancels nicely. And 0 times anything is 0, which gives me equals x plus 3. I can now move the x or the negative over the 3 to negative 3. And now I have x equals negative 3 for negative 3, 0 as my x-intercept. For y-intercept, now I'm going to replace the x values, right? I have 0 plus 3 here, divided by 2 times 0 plus 1. When you replace the x values with 0, I can solve for y, which is the y-intercept. F of x equals 3 divided by 2 times 1. So we got 3 over 2, or 0, 1.5 for my y-intercept. It's going to be right here somewhere. All right, now here, as we go about graphing, right, we have our two most important portions. I can look at the holes, I can look at the y-intercepts, all that information, right? I just want to make sure that I set the denominator equal to 0, so my vertical asymptote is at -1. Right, and I have my graph. Looks also very similar. It goes like this. It's pointing down. This one's going to go through this point. Right, and it's not very accurate, but it's just giving you an idea and showing us that we have a hole at -2 somewhere here as well. Yeah, we'll get more specific in our next video when we talk about our horizontal asymptotes, which is our next topic. Yeah, for now, can we find where it crosses the x and y axis? All right, let's see, one more example, and then we can talk about the domain of a function. Here, I want to show you how there's nothing to factor, nothing to simplify. So there's no holes in this function. I can go straight into the x-intercepts and the y-intercepts. Yeah. On the x-axis, y is 0, and on the y-axis, x is 0. So let's plug these in. Let's see what happens. Right? When I plug 0 for y, I'm going to get 0 equals 1 over x minus 2. To solve for x, we're going to get rid of the denominator, which means we're going to multiply the top by x minus 2. This cancels nicely. 0 times anything is 0 equals 1. What does this mean? What does it mean if we're trying to solve for the x-intercept and we get an error because 0 is not equal to 1, right? This means that there are no x-intercepts. Right? That value does not exist. When solving for x, the x's disappear. They are non-solvable, meaning there are none, right? Let's look at the y-intercept. So I can't put a single point on this x-intercept. And I'll show you what the graph looks like here in a second. When I look for the y-intercept, I'm going to replace the x with 0. So f of x equals 1 divided by 0 minus 2. As I solve, this turns into -1/2 or 0, -1/2. So the y-intercept will be right here. Yeah. And if we want to graph the function just to get a sketch a little bit, right, we want to know that there's a vertical asymptote. I'll change the color here. Hopefully it stands out. The vertical asymptote will be at the denominator at x equals 2. Yeah. And because there are no x-intercepts, the graph will look like this. It'll get really close to the x-axis, and then really close to the asymptote. And then on the other side, very similarly, it'll get really close, and then it'll drop, and it will not touch the x-axis because there's no x-intercepts. Yeah. It'll never touch it. We do have a y-intercept, but no x-intercepts for this one. Right, I just wanted to show you what that looks like on the graph when there are none. All right, let's talk about domain. So here I have a few examples. Right, when we're dealing with domain, we associate it with the set of inputs, right, the x values. So if we were trying to create a function and we were trying to graph this from scratch, we would choose different x's, plug them in to have different outputs, and then plot all the points. Right? Now, what x values am I not going to be allowed to plug in here, though? Well, I know that there's an asymptote here, so x cannot equal -3, and there's a hole here, so x cannot equal +1. So I can choose any number I want except for these because these are undefined. They don't exist. Right? Pick any number you would like. You're going to get an output for sure everywhere that you plug in a point. They all will exist. We have all kinds of points here. But if we plug in -3 and 1, we will not be able to get an output. Right? So we can say that the domain of this function are all the values are allowed to be graphed with the exception of -3 and +1. How do we say all the values? Well, we can say x is a set of real numbers such that x is not equal to -3 and 1. We can say it like that. Another way to say this would be we're going from -infinity to +infinity, right? Except these two spots. So we can go from -infinity all the way to -3. And we use a parentheses as opposed to a bracket because we never really touch -3. And then there's a union from -3 to 1. It doesn't touch 1, so we put a parentheses. And then from 1, it goes all the way to the right to +infinity. It goes that way. If you need help remembering this, go back to the very beginning of the videos where I talk about domain and set builder notation and interval notation and all that kind of stuff. This being set builder and this being interval. Right? Now let's look at the next one. So here, what do we notice? What x values are not acceptable? Well, we have a hole at x equals -2, so x cannot be -2, and we have an asymptote at -1. So we know x cannot equal -1. So we can say it several ways, right? We can say x is a set of all real numbers such that x is not equal to -2 and -1. Or, in interval notation, we go from -infinity all the way to -2. Parentheses, because we don't touch -2. Union, from -2, we go to the right. We have some numbers here, all the way to -1. It doesn't touch 1, but then it goes from -1, from this asymptote, to the right, to +infinity. Yeah. As long as you're comfortable with both notations, you'll ultimately be able to choose, right? Which notation are you more comfortable? Because you're now saying that there's two values that don't exist. Now, why are we focusing on the domain and not on the range? Because the values here on the y, on the output, the range, right? We normally associate this with domain, and this is range. Well, when we're dealing with holes and asymptotes, the domain determines the range, right? Whatever values I plug in will have an output, except these two locations. So if I'm already saying x cannot be -3 and +1, then I know that the range will also will not have an output at -3 and at 1, right? Because the output depends on the input. So us describing the domain is enough because we are automatically saying that these two numbers will not have part of the range as well, right? It won't create an output at those locations. Let's give another one a try. Yeah. What do you think about these here? What are my domains? And I'm just going to use one notation for now. X cannot be what two numbers? Identify the asymptotes. X cannot be -3, and X cannot be -1. Yeah. So we would say X is a set of all real numbers such that X is not equal to -3 and -1. What else over here? Well, on the right side we have no holes, but we do have some asymptotes at -3, and we have an asymptote at 2. It looks like it gets really close to it, but it won't touch it because it's a vertical asymptote, right? So X is a set of all real numbers except -3 and +2. That's how we would go about describing the domain. Now, would you be able to do this with given just the function? What if I just gave you the function like here? Let's go back to the beginning. Or let's give you a new one. I have another one over here. Let's say that I gave you a function. Could you find the domain of this function? How would you go about finding the domain without the graph? From this alone. Well, the domain is the set of all real numbers except what? The holes and the vertical asymptotes. So once you simplify the function, right? Once you simplify it, if you find that you have a hole, say at x plus 1 and x plus 1, I'm just making this up. This probably has nothing to do with this. If I were to factor and cancel, I know that since there's a hole, I'm going to put that value here, right? X cannot be -1. And then let's say that I have an asymptote at x plus 2. The vertical asymptote is at x equals -2. So then I would use my other location up here. X can also not be -2. Yeah, so from a function alone without the graph, you would look for the holes and the vertical asymptote to determine the domain. Notice how everything ties in together, right? The last few videos all lead up to this. And this video will lead up to the next topic as well, which is horizontal asymptotes. Until then, as always, I'll calculate.